So, hello everyone. My name is Emmanuel Bakare, and today I'll be taking you through what is a pretty easy networking problem. Um, so, the idea is networking stalemates. There's something called closed weight sockets, and the best way I can put it is that um, as you begin to play around with making requests to say databases and different things, there's a very weird way that all of this kind of makes sense. But before I dive straight into that, let me do an introduction. So my name is Emmanuel Bakare. I started a company called Baseline HQ Cloud where I build cost saving solutions. One of them is CostGraph. Please check out CostGraph. And I also do DevOps at Twilio. I'm a senior DevOps engineer there, and I basically manage everything from the on-premise stack, their AWS services, and all the fancy conversations with leadership and figuring out, how to make people happy. So, jumping in, like this is what we're talking about today. It's mostly TCP states, closed weight sockets, how they happen, why it's the client's fault, how to remedy closed weight sockets, and then some conclusions. So before kicking off, I'd like to put a disclaimer, right? Even though I talk about networking, closed weight sockets happen only on TCP. And the reason for that is because in TCP, the client and the server have to be in agreement with each other. So you can't make a request and then the server is like, it dropped. I'm sorry. Right. It's because of the fact that the server cannot just drop a connection that we end up with these cases, and TCP, enforces that contract. So TCP will be the focus today. Now in TCP, we also then get something called TCP states. So whenever we make a connection, and most of this I'll show you in a very quick demo, the entire like TCP connection lifecycle is modeled like a state machine. And what that means is that it kind of iterates from one state to another depending on like what you do. This is a very nice diagram kind of showing that state machine, right? Active means it's on the client, passive is on the server. So the client is your laptop, anything you make a request with. And the idea about this is that, as you can see, there's a lot of stuff that happens when you make a request. It usually starts from SYN. Everybody knows that SYN, SYNAC, then it moves to established, and then you have like this roundhouse circle of fin wait, closing, fin wait 2, timeouts. Like it's just really a lot of, transitions. Now, the problem happens on this passive close side, if you can see it, this box right on the bottom right. Right. And what happens is that sometimes that close waits, because it's passive, the server is basically saying, I got a request that you want to terminate this connection, but I'm choosing to ignore it. And that could be for different reasons. For example, your clients could die. Like your clients could just disappear, like network partitions. So now the server can't talk back to the clients, but it's stuck in there. So the question now is that the server doesn't close connections. And that's for very good reasons in the TCP spec, because the client might be trying to reconnect so that it can continue sending data, right? Remember, TCP has very strong transactions about like how you send packets and get it back. If it's fragmented, if it's broken, it will retransmit those packets. So so they basically went with let the client decide when the connection should end. And what that means is that if the server can't talk back to the client to be like, are you done sending what you're sending me? The server just waits indefinitely for life. And that closed socket can cause a lot of problems. So let's kind of get into it. The relevant TCP states I will talk about today is mostly things like closed, meaning there's no connection, it ended completely. Listen is what happens when you start a server on your laptop. Like listen is like when you open up a server port. And established is basically like, okay, all the connections have been made, the server and the client, they are talking to each other. And for simplicity, I just did the classic three-way handshake, which is SYN, ACK, SYNAC. But in some cases, you have some extra things like, the four-way handshake, with SSL, kind of coming into that, parlay of, how those connections get established. Now, the problem I had, and this is where the problem statement gets defined in this classic star approach. So you have a Redis server, and the Redis server is saying it cannot accept any connections. Why? Because we have a ton of closed weight sockets that have exhausted the connection pool. So when you think of servers, the servers can accept a maximum amount of connections, right? It's usually like dependent on how many things how you configure the setting on the server. Like some people know max connections. So if I say I set a max connections of 100 and 100 of them are in closed waits because the server died, nothing happens. So the client can't talk to the server anymore because the server has exhausted all its connections, which are now in close wait. And now it can't publish metrics. It cannot send anything. So everything just stops working. And the interesting thing about this was that it was caused by a bug in the Redis server. So we'll kind of get to that point. But the idea is when closed wait sockets happen, it's not that the server isn't running, it's that the server is unable to accept more connections because all the connections are not in established where it can process them. It's in closed wait where it's meant to end, but it can't end. So now everyone is like, server, give me more connections. Server is like, no, I've exhausted everything. And the client is like, I'm trying to connect. And the server is like, no, wait until the connections are open, and it can be. So let's push forward. What caused the break? We upgraded our Redis server, right? And everything just broke. And it was because of that. So restarting the server fixes it. And the reason is because as I will later show, when you create a connection, it's all bound by that instance of the server running. If you close the server, all those connections die. So again, sorry about the terms, about dying. Like the connections end, they terminate cleanly, and everything continues. But it doesn't mean that it always works out. So closed wait sockets happen when the server just really can't, just has wasted all the connections it has in closed wait, and it doesn't close properly. So let's dive in about, I don't think the fix is really a thing to talk about, but let's continue from closed wait and defining what it is based on that intro. So closed wait sockets happen when really the connection comes in and then the server is like, I'm trying to end this. The client needs to tell me if it has ended. The client can no longer talk to the server can no longer talk to the client, and the server is like, for the server to close, it's passive. The client has to tell the server, you can go. And the server is like, I cannot get that message, so it just waits forever. Here's a very nice diagram that I will describe it. So a client and server are trying to get connected. They do their three-way handshake thing. They're happy with each other. They're like, you are going to serve me today. That's what the client tells to the server. Now, everything goes into established, right? Because both of them can now talk to each other. The problem happens that the client are now connected, and the client is like, now I'm done. I want to end this transaction that we have, this connection that we've established together. It sends a fin packet. The client goes into something called fin wait 1. Now, the reason why it's fin wait 1 is because when people built TCP, they were like, you know what? Sometimes the client can be like, we need to close, but we're not ready to close. So you send the first, I'm trying to close. Then it establishes that, okay, fine, it's going to close. Then there's a fin wait 2, where it's like, I have basically cleaned up everything before I close. So now I can close cleanly. And then we can now terminate this connection, right? Because remember, TCP has strong integrity. There's transactions. So this is kind of like that, for those who know, like the three-way protocol for transactions, right? This is kind of like what they established. So you send it, the server goes into close wait, the client goes into close fin wait 2, basically saying between fin wait 1 and fin wait 2, I'll try to clean up everything so that I can close cleanly. Now, the problem happens when the client cannot respond or the server terminates the connection. And the reason why I say server terminates connection is very interesting, because sometimes the server can be like, okay, this, take for example, there's a client that is misbehaving. Sometimes you just want to get them off, like, please go. So the server can terminate connections if it wanted to. And what happens there if it then does that? Because that breaks the TCP specification. Remember, the way they built it was that the client should be the one to terminate the connection. If the server terminates the connection and it's in close wait, now the server cannot end the connection because it was never built to end connections. So basically, the client goes into fin wait 2. The server still stays in close wait because the server is meant to get a request from the client saying, I'm done. And what now happens? The client closes its connection. It's like, okay, I'm going to go away. And now the server is stuck waiting for the client to respond. But the client is never going to respond. And this is basically a stalemate. This is a deadlock in networking. And it is one of the most annoying problems about running. It affects every single server running TCP. And it's a very big problem. Most people don't have to deal with it because The cause is very simple to solve, but it's also very hard to replicate. So that's what I'm going to do now. I will take you through a demo. Now, this is the link to the demo. It's basically on my personal GitHub. It's TMR Closeway demo. And I will be bringing um, my terminal up to the screen so that y'all can actually see what I'm doing. So on this terminal, I have a couple things running, right? As you can see, I have established cowsay because it is only fair that I show you an image of a cow saying this is the client, my local laptop. Now, what does this do? I've got a couple of things here in like some hacker mode setup, but it's really nothing. I'm just showing you the number of connections. So these are all the TCP states you see day to day. You can see scene sense, you can see established, you can see listen. There's a bunch of things running here. And I also have my server. So this is a Raspberry Pi. This is what is going to be hosting our remote server for today. Now, if I show you what is in the server code that I've written, this is basically a closed weight server. And what did I do here? So when you build a server, it's really just fancy network engineering, right? With sockets, right? So what I've done here is I've replicated my own TCP socket. I've used reuse address, sock stream. All this is like classic like network programming 101. But I've also done something cool here. I've kept a list of open files. So I want to basically trigger a file resource exhaustion, right? I want to showcase like the problems closed weight causes. Because when closed weight happens, what happens is that the server opens up a socket for that particular session, but it doesn't clean it up. So what happens? There's memory attached to that session. There's open file handles here attached to that session. So what that means is that if you get enough closed weight sockets, your server can become more responsive, it can die, there can just be a ton of memory being used. And that was what happened to us. The ready server would die, we couldn't connect to the client if we were lucky, and the VM would just hang. Very, very strange problems. But how did I do it? So here is what I'm doing, right? So you can notice here that I'm killing. So what I do is that whenever a request comes in, I basically fork it. So I'm doing the classic Nginx style, create a fork for every single session. And I'm handling the connection, then I'm terminating, right? I'm saying 6 exits, blah, 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 blah. All that kind of cool stuff, right? Clean exits. Here, I'm basically saying, okay, fine. I want to kill the process on the server that is handling that client connection. And I basically want this to continue forever. So you can imagine this to be like a very weird way of simulating a network partition. The client was able to connect, but now we cannot send the request back because the client has died. So this is all I'm going to run today. And what am I going to do is a very simple thing. I'm just going to run Python closeweight.py. Now, why is this important? I am going to show you in a second. So let me restart this. So I have two things here. There's one that is running on LSOF. There's one that is running on SS, right? So let's kick off. I am going to come here and I'm basically going to do nc localhost 5555, right? So as you can see here, this is me testing this out locally. You can see this is my client. This has established a connection here. You can see my guy has handled the connection. But in my case, I've killed it, right? I've said, okay, fine. Whatever process started for this has died. Now, if I cancel this, you can see, oops, we have a closed weight socket. You see that this file is still open, right? Because it didn't clean up, cleanly, right? Everything is still running. So I could come here and then I could grep, right, for this particular session, right? So let me see how I can do that. You know what? I'm gonna do grep close weight. No, let me see what this is gonna give me first. Yeah, okay, I don't even need to do that. Like, it's very simple here. So as you can see, this is in closed weight, right? This is basically the process I'm running. And you can see this is 747851. This is a process I started basically when I ran NC. Now, as you can imagine, this is a process. It has CPU attached. It has memory attached. Meaning that every time a closed weight socket happens, there is memory on my server that is being allocated to nothing. It is idle. It is a waste of resource, really. And there's also open file handles attached, which means that I can see it here. Now, for those who do not know, whenever you run Linux or any operating system, right, there's a limit on how many file handles you can open. They call it open files. You can see here, I have 1024. Now, that's not really a lot, right, per process. So that means that if I send enough requests here, I should be able to break my server. And that's what I'm going to do today, to simulate just how badly it affected us. So I have my laptop here and I'm also doing the same thing. I'm watching for connections I've started and everything else. This is my local. If I run this, you see that this is running my Fedora laptop with the host name set to my router for whatever reason that exists. I think I played around with some stuff on that. So what I'm going to do now is I'm going to run this guy called client no block. And what this is going to do is that it's going to simulate me sending a request using SOCAT. I'm going to send 2,000 requests. Remember, our limit is 1,024, right? This is going to be a very, very, very slow break. But the idea is that if I send enough requests here, this should break just fine. So let's run this, right? So I'm going to send 2,000 requests. As you can see here, I have finwait 1, I have finwait 2, because why? My client is sending requests and it's waiting. And then at a point, all of these, they are going to go away and they are going to die. So this is what happens when you send requests and then they terminate, right? It's done sending the request to the server. And now it's gone into finwait 1 and finwait 2. If you add this, you see that this is 2,000. Now, if I go back to my server, you can see we have some close weight sockets, right? We're at 959. We're hedging up to the bets of, oh my God, see, error opening file. So now I can't open files on my server. Now, let's imagine that this was, say, S3 that was hosting whatever, right? Because of this small bug, that small bug that I had when I wrote my server, now I have a limit. I actually have throttled my server in a way by just saying, if I can open 1,024 files, and because of this bug I have in the server, now I can only accept 1,024 requests, and then everything just breaks. Back on my client, as you can see here, this guy is still waiting. It is going to wait forever. And if I come here and then I check, like, let's see if I can find SOCAT. Right, let's see. Do I find SOCAT? No. My client has disappeared, right? There's no client again. This has died. This is gone. This is done and dusted. But you can see remnants of the request, even though there's no clients that this can talk to anymore. And as you can see, the server is still holding on to those requests. And if I run else of I and I grab close weights, you'll see a bunch of requests that have been opened, right? I can even just show you PSOX and let's see how many servers we have from Python forking this process. Quite a lot, right? You can see. So for every single process that this server created to handle this, I have basically seen a lot of requests. If I run htop, I'm at 7 gigs. Now let's close this server. Let's terminate it. Let's kind of move on from whatever this is. So I'm going to come up here and I'm going to stop the server. And you're going to see just how much memory this 2,000 request I simulated was using. Just about 2 gigs of memory for doing nothing, right? So that's the potential of what closed weight sockets can do. That's the impact they can have on the environment. That's how dangerous they can be. And guess where the bug was? The bug is literally just here. This os.kill. That's all. Now, obviously, this is a lot simpler. When you're running like Redis, Postgres, or anything, and they have to manually build their own networking stack, because remember, Postgres is a custom protocol on TCP, right? Postgres wire. You have Redis, you have MongoDB. So there's like various people that actually do this day to day to build databases, to build queues. Everything that has some distributed networking setup ends up with some programming similar to this, right? Emails, like everything else, right? But that's just like a quick demo on like how closed weight sockets work, how they happen, how dangerous they can be. As you can see, I ran 2,000 SOCAT connections, 2,000 SOCAT connections from my laptop. They all disappeared, but the remnants of those requests were still on my server, and I basically had to pay for it, literally, in memory. So some people end up scaling their servers. I think when I was at AWS, we ended up scaling the servers. We did a lot of things, right? But the bug was actually in Redis. And as you can imagine, we can't patch Redis. So that's an even bigger problem to solve. That's just how difficult closed weight sockets are in reality, and just how much work you can actually get from just like having them, in your environment. So let's get back to the slides after that demo. I hope it was clear enough, like just how closed weight sockets work and how they happen and how dangerous they can be. So here you can see this is just a very simple state diagram. Closed weight will wait for the app. If the client dies, it will never progress. And then basically you end up in this situation. So let's round off stalemate sockets. I've already kind of explained this. Close weights, they're basically a stalemate. If the client dies, the TCP specification says the client must continue, the server terminating. So there's really nothing you can do. It is a very, very, very dangerous problem to have because there's almost no solution. There's literally almost no solution for it. So it's always the server's fault. If the server terminates the connection, the idea is that the client has to basically continue its life cycle, right? This client is always going to do its thing. And this is distributed consensus. There's a lot of ways you can think of the problem, right? It's one of those things that they never really solved. So if the client has gone, then the server can continue and it just continues like that. So moving forward, the idea is that I've already kind of talked about this fin wait one, fin close wait, and everything else. It's basically just the same passive closing. But as you can imagine, close waits, they cause memory leaks, they cause resource leaks, they cause a lot of problems, as you can imagine. Damn 2 gigs of memory just for doing nothing. They block connections. So as you can also notice, if I needed to open a file handle to process that connection, like say S3, where I need to read the file and respond to the user, unlike my own very dumb network proxy that just takes in the request and goes oopsies, that's a really big problem because now the entire server is broken, right? You can't read files, you can't do anything. And here's another simple diagram. If the client is like, okay, fine, it even wants to reconnect after that 2,000 requests went through, it is not really possible because the client is like, I already have a connection with you, I guess, in the past, and there's nothing I can do. It needs closure, and the client can provide it. And these clients could be, unlike my laptop, thousands of hosts in a data center, like how it happened in AWS, or millions of hosts, like what we're doing today, where we're streaming off this site. It's a very, very dangerous problem. Once you have one closed weight socket, it can expand into full resource exhaustion across your entire fleet, all because of one simple server bug. So how to remedy it is very hard. The server can't close weight sockets, right? So in the client, you could say, okay, fine, there's a connection, keep alive. If the client has waited for like 5 minutes, close the connection. That can happen. And the client can do that just fine because the TCP spec basically says the client controls the connection lifecycle. The client will always make the request. The client can easily terminate the request. But the server has to wait for the client to be ready to terminate the request because the client is always sending data back and forth. If it can't, the server doesn't move. So because of this, the only way to fix it is by actually patching the server. So like what I did, if I removed that os.kill in the previous slides, that would fix it. But the problem is, imagine you are patching Redis server. Now, Redis is an open source product. You can't just go patch it. There's some security people that are going to be up your neck. There's a couple reviews down the line. So there's a lot of administrative and even programming efforts to find it. When we did this, we ended up sprawling on GDB because it looked like a deadlock, right, from a networking perspective. But it wasn't a deadlock. It was a networking problem. Keep alives don't work. The server is not going to close a socket in close waits. So the best you can do is restart the server, monitor it, or patch the server, which is easy or hard, depending on if you wrote it or not. And those are the two problems I have here. Deploy monitoring or fix the clients. And remember, close weight sockets, they show up in very weird ways. If you run a server, I'd advise you to always check if you ever experience this kind of problem. It's a quick check with SS, as you can see at the bottom of the slide. For those who are actually aware of how you can monitor it. If I go back to this terminal, all I need to do to be sure that I can watch and see close weight sockets is to do something called ss-tcp states close-wait. And from here, as you can see, I can see all the close weight sockets that were open long before I started this session. So this is how you can also then find close weight sockets, investigate them, and be sure that you also then have a way to find where they are. So with this, I kind of come to a close on the entire discussion. Close weight sockets are a problem that manifests with a bad client terminating early, but a server closing connections too quickly. There's no fix. It's one of those things that everyone is like, yeah, we built in the problem. But the fix is usually because of buggy code. So they're like, you know what, we don't need to fix it. I've left some references to some of them, some folks on Cloudflare wrote a really great article on it. And yeah, that is pretty much my entire talk. I will be open and taking questions. Okay, so it is. Yeah, so it looks like I have actually concluded this quite early. So when you console, I'll leave it over to you.
Hi, Emmanuel. Thank you very much for a very wonderful talk on networking stalemates. I'm sure we all enjoyed it and learned a thing or two. So everyone, please put your question in the chat box, in the Q&A rather, so Emmanuel can answer them. Also, while you're doing that, we asked you to fill the survey in the chat, pinned in the chat. So tell us what you liked about the session, if you enjoyed it. We would love to hear from you. Thank you.
Oh, no, thanks for the session. Um, I kind of missed if you talked about how to um, like monitor for this. Is that alerts we can like set up ahead of time for issues like this, etc.
Yes. So you would have seen there was a command I left on SS. So the thing is that the TCP states, you could probably get it with node exporter. Like it depends on what kind of system it is. Hence why I went to like the more generic command line case. But it's something that is quite easy to monitor. And it depends on where up the stack you are. So even though I showcased it like happening on the code side, it could also happen on the load balancer side. Um, there's something called DSR, domain server return, where like the server that processes the request, it doesn't go back to the load balancer. It just sends it to the client that requested it. Like say your phone goes to TikTok, TikTok load balancers process the request. Rather than it going back to TikTok load balancers, the data is just sent directly to your phone. That can cause closed weight sockets in its own way. Like say, for example, the ISP changes your public IP address. So there's a lot of ways that monitoring it is hard because different pieces of hardware along that stack make it extremely hard to know how to do it. But this basic idea is SS is a good way if you run the server. And then for most others, you kind of have to build your own tooling around it, depending on what vendor it supports, what part of the networking stack it is. It's just one of those interesting problems that no one really wants to solve. If you never hit it, if you've never had the problem, then good for you. It's not something you will ever see unless you're lucky, like me.
Yeah, it may something worth checking. But yeah, thank you for the talk. So we have some questions now, so I'll leave you to take them.
Yes, we have a few questions here. So Chikuma says, I know you said there is no solution, but are there any mitigations, like ways to make sure this really happens?
Yeah, I would say it is usually just writing good code. Like you notice the example I did, you basically are the owner of the problem, right? If it happens, it usually happens because someone basically did something they shouldn't have done. Like in my case, allowing the server close the connection where the client should dictate how the connection should close. And for that, it's left to the implementer. So a way to mitigate it is basically restarting the server or manually closing the sockets. Like in my case, you can actually close it with like that dash dash kill on with SS. That's one way to mitigate it. But the problem with closed weights, as you can imagine, is if more clients keep making requests, more of those connections will just go into closed weight and exhaust everything. So there's no mitigation. There's also no solution. So it's just one of those problems that when you have them, everyone is just like revert back to the last stable version of the server. Like it is really just that. Or you deploy a watchdog that closes all those connections for you. But that's more a hack. And even when I pitched it internally, no one accepted that. Okay.
All right. So another question is from Joseph. It says, I am wondering if there are no CCTL configs to tweak to limit the number of closed weight sockets can be alive concurrently. Did you get that?
Yes, very good question. And it is also a very hard thing. So here's the problem, right? The problem is that that is a very valid way you could solve the problem, right? You say this CCTL config controls number of close weights. The question I have is that if I have 10,000 requests and those requests become in close weights, what happens then? My throughput on that server is extremely high. You end up with a problem, right? How can you tell the difference? The question is you can't. You might say, okay, well, let's wait for the close wait and let's see if it's within 5 minutes. The question I also have is that what happens if the client wants to terminate the connection, but it has a very long period to basically say, okay, fine, I want to basically, clean up that, right? TCP has very strong guarantees to say that you can never lose data, right? It's part of the specification. So it rarely ever happens that you build the fix without breaking something else. So there's really no fix for it, right? Most folks have just observed that this problem only happens when you write buggy code. So they're like, it's not really the TCP spec that's broken. It's it's your server. So go fix the code, right? You get it's like it's not a problem on the spec side. The client can handle working around this with like keep alives and terminating long running connections so they don't go into close wait anyway. That's what most people do. They set like connection keep alives with the same cctl config you've mentioned, like tcp4.keep alive and that's got time. There's like a couple of them. So to answer your question, it cannot be done on the server because TCP enforces that the client should be the one to do all of that. So when the server can, so if the server tries to do that, there's a whole lot of problems you open up.
Okay. So another question is from Naya. It says not totally related to this, but what other quote gotcha situations have you ever run into that are networking related?
Okay, this is a very, very nice one. Okay, well, like I could go on a ramble, but I'll just say the difference between using a layer 4 and layer 7 load balancer can be interesting. You can get almost 100% um, performance by just running on raw TCP packets than using, say, HTTP. There's something called encapsulation. It's a whole interesting ball game. But the idea is that there's some tricky, interesting ways to hack and play around with it. The thing is packet sizes. HTTP has some bloat. So if you send smaller packets, you get better performance. That's another gotcha that I mentioned. Oh, yes.
Okay, so we have just a minute left, so I'm not sure if we can take this particular question. So it's from an anonymous. It says, does using HTTP2 or gRPC reduce chances of close weights since
No,
connections are pooled and multiplexed instead of short-lived?
no. You will always end with close weights, even when they're multiplexed, because all it takes is for the client to send a fin packet. So if my client, say, dies really quickly, and the client goes into close wait, it will still happen. So as far as it runs on the TCP specification, it is affected by close wait sockets, irrespective of whether they're pulled, multiplexed, short-lived. As far as the connection happened, it is always going to, like, there's always a close wait state transition before it's, closes, basically. Yeah, threshold or alerting strategy. No, there's really no way to benchmark it. And I've explained that from Joseph's question. There's no way to be able to say this number of close weights connections are bad, because you can have a lot of connections that all transition to close weight normally, and the client has to basically close them. So you like there's really no way. Just build your own tooling around it. It's usually a bug in your code, so they never patched it. Yeah, that's all for me.
All right, thank you, Emmanuel. Thank you, everyone, for your questions. We've come to the end